Hello everyone. Today I'm glad to share with you our recent work, morphling, fast, near-optimal auto-configuration for cloud-native model serving. Companies are increasingly deploying large machine learning as a service cloud for model training and inference. In a typical machine learning as a service workflow, deployers design and train machine learning models offline. The trained models are then published in the cloud to provide online services, typically running in containers. Many model serving systems are developed to provide the model deployment in the container for improved performance and reduced costs. Existing model serving systems support functions such as dynamic batching, inference buffering, replica auto-scaling, and auto-selection of model variants. However, we find that efficiently deploying the inference services in the cloud is still challenging. In specific, given a trained model, the cloud providers also need to specify the resource allocation and runtime parameters for each model serving container. For example, we observed that in a production cluster of Alibaba cluster, an inefficient model serving configuration results in very low resource utilization. For example, in this picture, nearly 80% of the CPU cores are not used. In light of these problems, our goal in this work is to design an efficient approach that can quickly find the optimal configuration for an inference services. Inference services usually run in containers, and we measure the container's serving ability with its peak request per second (RPS) it can serve without violating the response time service level objective. The peak RPS can be easily measured by stress testing tools, and our production systems use the peak RPIs to determine the required number of container instances for each service. Given a model serving container, cloud operator needs to specify its resource and runtime configurations. To quantify how each configuration may affect the serving ability, we profile some open source and production machine learning inference services. We stress test their peak RPS under various configurations. As we can see, we find that a good configuration yields over 10 times RPS than a bad one. We also observe that these configurations may vary by different dimensions. So, given a well-trained machine learning model, the cloud providers need to find the optimal resource allocation and runtime configuration for each service. Formally, consider a configuration vector with IM-tunable hyperparameters. Our goal is to find the optimal configuration combination that maximizes the objective function fx. As we can see, it's essentially a hyperparameter tuning problem, and many auto-configuration approaches have been proposed. One common approach is to find the optimal configuration based on workload's past executions. For example, Google's Autopilot learns the optimal configurations by analyzing their trace data. However, we found that machine learning frameworks such as TensorFlow occupies all the available the GPU memory size when running an ML workflow. So, monitoring tools such as NVIDIA SIM always observe the full memory usages, and even though only a small number of the GPU memory size is used actually. Another approach is to sample a small number of configurations for performance evaluation, such as black box search, white box predictions, and similarity-based searches. We found that these approaches require sampling a large configuration spaces before finding the optimal configuration. So in this work, we present morphling, a fast and near-optimal auto-configuration framework for cloud-native model serving services. Our key observation is that the hardware resource allocation and runtime configurations in machine learning model serving have a general performance impact to a wide variety of services. For example, to run an inference service, there is a minimum requirement of GPU memory size to load the serving model. Further increase in GPU memory size allows it to serve larger request batches and hence a higher throughput. This motivates a fast auto-configuration approaches using meta-learning techniques. In specific, we formulate the optimal configuration search as a few-shot learning problem, and it solves it with a recently developed model-agnostic meta-learning, aka MAMO technique. In particular, morphling trains the meta model offline that captures how each inference serving performance may changing generally under varying hardware and runtime configurations. This meta model provides an informative prior to the configuration search and is used as a good initialization of the learning process. Giving a new inference services, morphling performs online few-shot learning. It samples a small number of configurations and uses as a preferred result to adapt the meta model to a new service. We have implemented morphling as an easy-to-use auto-configuration service in Kubernetes, which is open sourced for public access. Morphling is now also integrated into the kubedl project as the CNCF sandbox project. In specific, morphling exposes common interfaces that abstracts away the heterogeneity of the model serving frameworks and serve deployments. Users implement these interfaces by specifying the serving model, the tunable configuration parameters, the optimization objectives, and the sampling budgets. Morphling then automatically tunes the configuration to obtain the optimal serving performance. For evaluation, we evaluate morphling on both Amazon EC2 with 42 popular open source models provided by TensorFlow Model Zoo, such as image classification and language processing. Morphling has also been deployed in Alibaba production cluster as the default auto-configuration service for efficient inference serving deployment. As a result, morphling quickly determines the optimal configuration by sampling less than 5% of the large search space, consisting of over 700 configuration candidates. In comparison, existing auto-tuning approaches require to prefill quite more configurations to find the optimum. Morphling's high efficiency is attributed to its ability of quickly adapting to the meta model to a new inference workload. To illustrate this problem, we considering tuning two configurations knobs, GPU memory size and the maximum batch size. The figure on the right top shows that mapping plans given by the initial meta model, the adapted model after 8 initial samplings, and that after 28 samplings respectively. The meta model after sampling a few configurations is quickly adapted towards ground truth. Besides, the high performance and low cost of morphling are not tied to a particular objective function, but generally applies to the broad wide of objectives. To show this, we define another two tunable objectives, referring objective number 2 and number 3, as shown in the right figure at the bottom. As we can see, morphling retains the advantage over other baselines, always returning the optimal configuration with less than 5% of the configuration samplings. To summarize, we present morphling an intelligent configuration tuning system for machine learning model serving deployments. Our experiments on both open source and production services show that morphling selects the optimal configuration with much lower search cost than existing solutions.